Awesome. So yeah, hope you all can see my screen. So this is Multimodal Weekly, a webinar series hosted by the team at 12 Labs. We've been meeting on a weekly basis over the past 2 years or so, and here are some of the topics that we tend to cover on a weekly basis. We have researchers come and talk about their focus on multimodal AI and foundation models. We have community members talk about their different applications, building different verticals. Sometimes developers, partners talk about the specific video projects that they build on. And obviously members from our community share tutorials and guides on how to use our platform and API. For today's, here's some of the previous session that we cover from different, topics, right? You had video retrieval to video streaming to captioning, some of the work on like the more exciting stuff around test time scaling, agents, world models, etc. So yeah, today we have a pretty, short and straightforward session from Dohun Lee. He's calling from Korea, right? So I think it's pretty, I think either too early or too late for you. I'm not sure, but he's gonna give a talk about his recent papers called a framework for enhancing video generation at inference time via a teacher model. Then this framework that he built is called VideoGuide, and I think it's focused on the domain of diffusion models, right? Like looking at text-to-video diffusion, and I think specifically it leveraged some pre-trained video diffusion models as a guide delivering some early-stage inference, therefore improving temporal quality of the AI-generated video by interpolating the guiding models denoise samples into the sampling models denoising process. I think, yeah, like a lot of exciting work currently happening in that space of video generation. So I think some of the key learning from here will be very valuable for us from the video understanding side of things to understand as well. So with that, yeah, quick logistic note for the attendees, feel free to send your question in the chat, and then we'll have a short Q&A with Dohun after you finish. So without sharing my screen, and yeah, Dohun, feel free to go ahead, share your screen and start your presentation.
Yes, okay, thank you. Okay, can you see the screen well?
Yes, I can see it.
Okay, I'll now start my presentation. Hello, everyone. My name is Dohun Lee, and today I'm excited to present under the title A Framework for Enhancing Video Generation and Inference Time via Teacher Model. This presentation is based on our recent work, VideoGuide, Improving Video Diffusion Models Without Training Through a Teacher's Guide, which was accepted to CVPR 2025. In this talk, I will walk you through how we can effectively enhance video generation performance at inference time without additional training by leveraging the guidance from a teacher model. First, before we introduce our method, let me start by explaining why we did this research direction. Recently, we have seen a surge of training-based solutions aiming to enhance video generation. These include words like 3D-aware video generation, video jam, or introducing the flow objective, and the introduction of scalable video diffusion transformers. All of these approaches focus on improving the model's performance through additional training. However, enhancing video generation at the inference stage itself has received much less attention. Despite this, we believe it is a highly important direction as it offers a new and efficient pathway to push the performance of video diffusion models even further without the need for expensive retraining. In addition, within the video diffusion models, there are specialized architecture designed to generate only certain types of samples or specific styles. However, these architectures often come at the cost of general video quality, such as temporal consistency and motion smoothness. This degradation happens because the focus is too narrowly placed on achieving the desired output while sacrificing the broader conditions that a good video should satisfy. A good example of this is, I think, Animate Diff. As you can see in the video on the right, while it can generate cartoon-style videos, but you can also observe that the subject appearance changes or shifts between frames, highlighting a lack of temporal consistency. Before diving into our method, let me briefly go over the background and the related works. In the field of inverse problems, applying guidance during sampling is often viewed from the perspective of an optimization problem, where we aim to minimize a specific loss function during the sampling process. For example, in the work Manifold Constraint Gradient MCG, it is argued that guiding the denoised estimate effectively constrains the sample onto the diffusion space manifold while minimizing the loss objective. However, taking gradients directly with respect to the ZT requires the gradient of the model itself, which is computationally very expensive. To address this, decomposed diffusion sampling, called DDS, introduces an approximation technique where the gradient is taken with respect to the denoised estimate instead of ZT, significantly reducing the cost. Another notable inference time approach method is free-init, which focuses on reducing the training inference gap by reinitializing the initial noise using a frequency filter. This method enhances temporal consistency, but as you can see in the video on the right, it also suffers from noticeable image quality degradation. This highlights the trade-off between temporal stability and spatial quality that still remains an open challenge. Next, let me introduce the main paradigm of our video guide as shown in this figure. In the diagram, the upper gray area represents the standard inference pathway of a diffusion model, where we follow the typical sampling trajectories. What we propose is to introduce an additional path by leveraging either a self or another video diffusion model. This teacher model generates an alternative sample, and through interpolation between the original and the guided sample, we are able to create a more consistent and higher quality video, which is then passed on to the next latent step. In this way, video guide acts as a plug and play guidance module during inference, contributing to improved video quality without any additional training. In the following slides, I will explain how this approach is theoretically motivated and how we derive this process. To begin with, in order to tackle the video consistency problem, we approached it from an optimization perspective and introduced a new objective function. Since real videos are inherently temporally consistent, we assume the existence of a model, which we denote as psi, that can predict the noise in a given noise input in a single step. Under this assumption, when we input a real video that's 0 into the diffusion process, the difference between the model's prediction and the ground truth noise should approach 0. Conversely, when the input is far from a real video, this difference becomes larger. When we incorporate this new loss into the conventional optimization framework and take the gradient with respect to the sample, the optimization process naturally leads to an interpolation form between the sampling model, theta's denoised estimate, and the teacher model, psi's denoised estimate. In other words, to minimize the consistency loss is by interpolating the output of the sampling model and the teacher model at each step. So far, we have assumed that psi is a model that can accurately predict the noise epsilon when a real video is given as an input. In other words, the most ideal form of psi would be a model capable of producing accurate noise estimates in a single step. A representative example of a such model is the consistency model, which is explicitly trained to predict noise in a single step. However, training a consistency model is extremely costly and resource intensive. To avoid this, we propose a practical alternative. We can approximate psi's estimate by learning multiple sampling steps of the original diffusion model itself and using the resulting denoise estimate as a proxy for the consistency model's output. This allows us to bypass the need for costly retraining while still leveraging the benefits of teacher-guided sampling. If we look closely, our loss objective is very closely related to the score distillation sampling objective. However, it is well known that SDS optimization often leads to blurry outputs due to over-optimization or mode collapse, especially when applying over multiple time steps. To address this issue, we borrow an idea inspired by FreeInit, which introduced a low-frequency filter for noise reinitialization. Similarly, in our video guide, we apply a low-frequency filter to the noise during the early time step of the diffusion process, allowing us to accelerate the convergence toward more consistent samples while mitigating the blurring artifacts commonly observed in SDS-based optimization. Okay. In our framework, Psy can be flexibly implemented using any video diffusion model, not only itself. If we use a stronger or more capable video diffusion model as Psy, it will naturally generate samples that are better aligned with real videos. Therefore, when we reconstruct the guided sample ZT, we allow the guidance model to follow its own diffusion noise schedule and produce its own denoise rate Z0. We then perform interpolation between the original model's estimate and the guidance model's estimate at time step t, effectively bringing the sample closer to the distribution of higher quality videos as represented by the guidance model. Also, it's important to note that the epsilon prediction we use here are all conditioned with text prompts using classifier pre-guidance. In fact, we can also apply the CFG++ algorithm, which has shown to work particularly well in our video guide framework. The key difference with CFG++ is that during the renoising process, when the standard CFG applying the renoising process into noise itself, but in the case of CFG++, performs the renoising using unconditional noise. This helps to maintain a smoother and more stable sampling trajectories, and in our experiments, video guide combined with CFG++ consistently produce better results compared to standard CFG. Yes, let's talk about the result of our video guide. Compared to live video generation, our method significantly improves subject consistency while preserving overall imaging quality in quantitative metrics. In contrast, as shown in FreeInit, FreeInit does improve temporal consistency, but it also causes a noticeable degradation in image quality. Also, let's look at the video example below. The left shows the result for animative alone, and the middle is the animative combined with the FreeInit, and the right is the animative combined with our video guide, where you can see the subject consistency is improved while maintaining the high image quality. Also, here is more example. You can see also more examples in our project page, linked the upper link in URL. Also, we do many ablation studies for finding the hyperparameters. As we expected, increasing the interpolation scale, meaning that blending more of the guiding model's output leads to improved performance. However, if we mix too much, the result starts to heavily resemble the guiding model's own generation, which is why we empirically limit the interpolation scale to a maximum of 0.5. Additionally, we found that increasing the number of diffusion steps where interpolation is applied also improves the result. This is because applying guidance across more steps allows the models to better refine the sample towards higher quality. Similarly, using multiple guidance samples and selecting the best one further improves the generation quality. However, it's important to note that all these improvements come with a trade-off of increased inference time, so there is always a balance between quality and efficiency that needs to be considered depending on the application. Another important application of our video guide is prior distillation. For example, when using animative with a Dreamboot model fine-tuned on very limited data, we observed that when prompted with the word frozen, the model almost always generates ELSA due to the strong prior bias from the small data set. However, when we apply our video guide-based approach, the output shifts to a frozen river without ELSA, effectively removing the unwanted bias. This demonstrates VideoGuide's ability to inject and distill prior knowledge from the guiding model, even in low data scenarios, enabling the generation of desired sample that the base model alone would struggle to produce. Also, why do we apply the low frequency filter, specifically in the early time steps? While applying larger interpolation steps does improve the consistency metric as shown in the figure, we also observed that beyond a certain point, the imaging quality starts to degrade. To avoid this degradation, while still benefiting from the consistency improvements, we apply a low frequency filter only in the early time step of the diffusion process. This allows us to accelerate the generation of consistency samples while preserving the finer details and high image quality in the later step. Okay. Additionally, it's important to point out a key observation regarding standard CFG and CFG++ in our method. In the early time step of diffusion, standard CFG tends to produce denoised estimates with strong color saturation. This leads to poor mixing behavior during our interpolation process in the early time steps, as the samples are already biased and unstable. In contrast, CFG++ produces much smoother and more gradual denoise estimate during these early time steps. This makes the interpolation process more stable and effective, resulting in better overall sample quality. Interestingly, while in other methods, standard CFG often performs better. However, in our VideoGuide framework, CFG++ consistently outperforms CFG due to smoother transition and better compatibility with our interpolation-based guidance strategy. Of course, our method also has some limitations. First, it is challenging to apply our approach when the teacher and student model use different variation autoencoders. Since many modern diffusion models have their own VAs, it becomes difficult to directly apply VideoGuide across models with incompatible latent spaces. In such cases, self-guided sampling remains the only practical option so far. Second, also our method still struggles with severely corrupted samples or highly complex physically plausible scenarios. For example, in situations that require accurate modeling of multiple interacting objects such as washing dishes, our current interpolation strategy alone is not sufficient to generate physically correct interaction. These cases would require more sophisticated scene understanding, which remains a future direction. So to address the first limitation regarding different variational autoencoders, we believe that designing a future roadmap for extending VideoGuide beyond shared VA spaces is an exciting research direction. One potential approach is to fine-tune a student model that already has certain strengths using reward models such as VLM-based motion quality estimator and applying GRPO fine-tuning to directly optimize for specific rewards. However, it's important to recognize the well-known issue of capability degradation in GRPO-based methods. For example, when applying the GRPO to optimize aesthetics goals in image diffusion models, the images indeed become more aesthetic, but at the cost of reduced image quality and weaker text alignment compared to the base model. To overcome this, instead of naively using the GRPO fine-tuned model for sampling, I think we propose to use it as the guidance model within our VideoGuide framework. This allows us to leverage the enhanced motion quality from the reward model while still preserving the student model's original capabilities, and at the same time, it mitigates the VAE compatibility issue. We believe this is a promising and flexible direction for extending VideoGuide in the future. So in conclusion, in this work, we introduced VideoGuide, a training-free and inference time framework for improving video generation by leveraging a teacher model's guidance through interpolation. There are two key strengths of our work. First is it improves the subject consistency and motion quality without degrading the image fidelity. And second, also, our algorithm is very flexible. So we can use the self or external video diffusion model as our guidance model. However, some open challenges still remain, such as addressing variational autoencoder space compatibility issues and exploring also broader applications of our interpolation scheme VideoGuide beyond the current scope. Nonetheless, we believe our approach opens up a promising new direction for advancing inference time video generation, enabling better performance without sacrificing the model's general capabilities or requiring costly retraining. Okay, thank you for listening. Okay, thank you. Okay, any questions?
Yeah, sorry about that. Hey, thanks again, Dohun, for going over the presentation. Yeah, for the audience, if you have any question, please unmute, and we probably have like about 3 or 4 minutes left until the end of the webinar. So yeah, if you have a question about his workflow video, just ask a question and put in the Zoom chat. In the meantime, would you mind going back to the previous slide about the future direction and limitation?
Yes. Yeah.
Yeah.
Yeah, I don't know why.
GRPO. What is GRPO stand for?
GRPO is the reinforcement learning. However, in live case, when training other models, we need some value-based models, value creating models in reinforcement learning. However, in the framework of GRPO, they don't need any creating models, and they make some reference as the averaging the reward from the samples. So this is a framework that comes out from the DeepSeek algorithm. Yeah, into DeepSeek. Yeah.
Got it. And I think in this slide, you basically said that instead of using GRPO directly, you only want to use it as like a guidance method, right? To choose motion quality, right?
Yes, exactly.
Do you have any like qualitative results of VideoGuide?
That means this in the case of GRPO.
No, the qualitative results, like when you a VideoGuide.
Like this.
Yeah.
When does it switch over from moderate?
And also, this is also the code depleted, and in project based there are more regions. Yeah.
So animate deep and Lavi, and
Yes,
are the
Lavi
two
is
open source like a video generation model that you use to compare against, right?
Yeah.
Yes. Upper is the animate diff with Video Crafter 2, and bottom is the Lavi plus Video Crafter 2. Yeah.
What have you tried considering benchmark against some of the closed source API, like Sora or Luma Labs, those kind of runway, those kind of model?
Compared with the not apply just benchmarking
Industry.
the animative hours and the Sora.
Yeah, benchmarking VideoGuide against the industry solution.
I think it has I do not I did not do that. However, I think it will lose because the base model of animative is very worse compared with the other Sora and state-of-the-art video diffusion model. However, we can apply the VideoGuide algorithm in any video diffusion model. Also, we can. Also, I did applying in Open Sora in our VideoGuide, so so we can improve the Open Sora output quality using the VideoGuide.
Okay, that makes sense. Well, I think it looks like there's no question from the audience. So again, thanks Dohun for spending time walking over the presentation today. Appreciate your preparation and talking about video guide with our audience. The recording of the session should be available on YouTube in the next few days, and be sure to share that on with you so that they can promote it. Yeah, and then excited to see some of the upcoming work from your lab at KAI's around video generation, multimodal, and basically extension of this work.
Okay. Thank you.
Yeah. Thank you.
Thank you.